My name is Jordan. I'm here at the Old 100 Mine in Silverton, Colorado, almost 2 miles above sea level, and this is the chemistry question. Gold. 79 protons and 118 neutrons of pure shiny goodness. Gold has been valued since ancient times and led to the formation of the western United States as we know it. Prospectors would venture out in search of gold, panning in the rivers for hints of nearby riches. Gold panning is a method by which we use the density of gold to separate it from the rest of the dirt. We start by stratifying our gold to bring it to the bottom of the pan, and then slowly we're going to take off the top layers until we have some gold at the bottom. Eventually you get down to mainly black sand, and as you swirl you can see tiny amounts of flakes trailing behind. Looks like there's also a little bit of copper in here. If there were enough hints of gold, mines would soon open, with the purpose of digging that gold out of the ground. Before long, mines were popping up all over the West. I recently got to visit one such mine in Silverton, Colorado. This video will trace gold from the mine to its final bullion form.
And now we get to go inside the mine.
We descended over 1,000 feet into the mine, and the temperature dropped to 47 degrees Fahrenheit. For my international viewers, that's 300 meters and 8 degrees Celsius. Our guide showed us the quartz vein where the prospectors thought the gold was located. Of course, I was distracted at the time by this bluish substance. I later learned it was a mixture of copper sulfates and calcium carbonates. The level of the mine was 3,200 feet or roughly 1,000 meters below the top of the mountain. There were vertical and diagonal mine shafts that went up to the next level, 600 feet or almost 200 meters above us. We got to see the lifts that would carry miners between the levels. The miners would communicate by bell signals in order to keep the lifts running smoothly. To give you an idea of how cramped they were, here's me standing inside one. So how does one start making tunnels in the mine in order to get the gold? It all starts with drilling. Small holes would be drilled in circles around a center hole. All the holes would be filled with dynamite except for that center hole. This was done to create a weak spot in order for the rocks to collapse, not just crack and stay in place. We were shown how the drill was operated, and I warn you, it is very loud.
Lecture, guys. This is a 1940s column drill. See the column? Now this drill runs on air. It rotates that steel up front there that's got a bit on her to cut the rock, and you crowd it with a worm or screw mechanism, but you can drill a 6-foot deep hole in this hard rock in 7 minutes. Now I'm going to run this, guys. It's a little noisy. Going to run it long. Here we're striking the mine, drilling off the column. Here we go, guys. You ready?
After the holes were filled with dynamite, the fuses were lit starting from the center and working out so that the rock would collapse in on itself. If all went well, you had a tunnel going an additional 6 feet into the mountain and a giant pile of rocks to clear out. Of course, they had very loud machinery to do that as well. You will see later what happens to the ore extracted from the mine, but all the waste rock was taken out of the mine and dumped off the side of the mountain. All the boulders you see here are waste rock. You may wonder how miners were able to see in the darkness of the mine. The answer is that they used calcium carbide lamps. Calcium carbide reacts with water to form calcium hydroxide and acetylene gas, the latter of which is very flammable. However, controlled generation of acetylene provided just enough fuel for a tiny flame that was used to help miners see. The Old 100 Mine has somewhat of a sad story. There were a few small mining operations in the area around the turn of the century, but they never made a profit and eventually closed down by 1908. In 1967, the Dixieland Corporation bought the land and drilled 5,000 feet into the mountain, but recovered very little gold. The mine closed in 1973. Now we move on to the Mayflower Mill, where the ore from this mine was and other mines in the area was processed.
I'm here at the Mayflower Gold Mill, where all the ore that came from the mine, way up there, was processed. Shall we take a tour? Here we are at the start of the tour for the Mayflower Mill. It was built in 1929 at a cost of $375,000, and it operated from 1930 to 1991. This is the machine shop where anything that was needed for the mill was made. Okay, so now I am in the old tram room, and this is really cool. Let's look around here. In front of me you have one of the buckets that would be used to carry workers and ore down from the mine. 2 workers could fit in here, and let's see where they came from. If you look out, you can see, starting way down there and going way up the mountain to the mine where we just were. At full speed, one circuit would take 45 minutes.
These are giant crushers that would take the ore and crush it down into smaller pieces. The crushed ore would be transported via conveyor belts to the fine ore bin, which would temporarily store it.
These 3 chutes carried the ore from the fine ore bin up above us into the rod mill, which you will see next.
The rod mill tumbled the crushed ore with steel rods to reduce the size of the ore from about 5 centimeters to 5 millimeters or smaller. The ore would then move to the spiral classifier.
After passing through the rod mill, where it was ground up, the ore was in a sand solution that would come down this, the spiral classifier, where the coarser sand would sink to the bottom, and the finer stuff would stay on top and continue for further processing. This thing here is the ball mill. This was the final step of the grinding circuit. It took the coarser material that we saw before with the classifier and grind it down to the required fine sand to liberate the remaining metal sulfides. These are the gold jigs. Gold, silver, copper, lead, and zinc were processed here, but the gold was processed out first because it was the easiest to do and the heaviest. This is a mechanical method by which the heavy gold drops through the screen and continues on. It says the button to the left will activate the rocker. Let's see if it does. The lead flotation banks is where everything that was not caught in the gold jigs seen earlier was processed. Selective flotation occurred here, where pulverized sulfide ores are separated from other metals. This is kind of neat. Different reagents were used for each metal, and we had collectors that had an affinity for a particular metal, which will attach themselves to the metal into the air bubble that will carry the metal to the surface of the water to be skimmed off. And then there were also depressants for other metals that will keep it submerged in the bottom of a float cell. And then a frother forms the air bubbles. Here we can see the reagent feeder providing reagents for processing.
Because this is the chemistry question, I will name off all of the reagents used. Reagents were added as 10% solutions unless otherwise noted. When I say pounds as a unit, I'm referring to pounds of reagent per ton of ore. In the rod mill, they used 0.55 pounds of zinc sulfate as a zinc depressant, and 0.2 pounds of sodium cyanide, which is a zinc and iron depressant, as well as 0.025 pounds of Aeroflot 404, a collector for lead and copper. In the first conditioning tank, they used Aeroflot 303, a lead and copper collector, Dow Frother Z250 as a frother. Onto the lead and zinc flotation, they used the concentrated Dow Frother Z250. In the copper conditioning tank, they use sodium dichromate as a lead depressant. In the second conditioning tank, they use 0.5 pounds of calcium oxide, dry fed with lime feeder, as an iron depressant and pH increaser. 0.6 pounds of copper sulfate to adhere to and coat the zinc sulfate, and a mixture of Aeroflot 303 and 350 to collect the copper sulfate and float the zinc. And finally, chlorine was added to the tails to neutralize the sodium cyanide.
You see these paddles here. This forms a cell bank where lead, silver, and copper were concentrated and brought to the surface with these paddles. You will see the paddles run shortly. Here we see the end of the flotation process. Any remaining metal was picked up here and pumped back to the zinc conditioning tanks to be recirculated. All of the insolubles and the vast majority of iron, which was considered a waste product, were dropped down to a retaining tank, where it was picked up and pumped out to the tailing pond for disposal. This was the last of the flotation process. The mill had a recovery rate of 90 to 91%. Here is the pump deck. These pumps were used to recirculate the material in the flotation cells seen above. The big tank below is the zinc thickener tank. In the shadow over here, we have the lead thickener tank. These two tanks would have been full of water, and their purpose was to eliminate water from the mineral concentrates. And this eliminated about 90% of the water. Then down on the next level, each mineral concentrate was piped down to its own filter bank, and the filter wheels in constant rotation on an axle, they would pass through the thick mineral solution, with the vacuum drawing the solution onto the Cavis filter. The water passed on through the canvas to be discarded. The mineral unable to penetrate the filter was scrapped off before entering into the solution again on another evolution. The semi-dry concentrate dropped down to a holding bin directly below in the very last step of the milling process. This mill could remove most waste from the metal except for sulfur, which requires large amounts of heat and can only be done at a smelter. Here is the deester table. The material from the jigs was deposited in the holding tank sitting above this room, and the material dropped into a funnel and down onto the deester table, which would shake with a fresh foam of water washing down over it. Now here you can see the lighter particles were washed and separated from the heavier particles. The gold and lead stayed high on the table and separated into two distinct bands of concentrate. Most of the lead was saved with the gold, since the two metals are very close to the same weight and become mixed as they came together, and they would fall down off the end of the table. Here you can see it at work. Here's the amalgam barrel, where the gold and silver and all the ore was mixed with mercury, which would pick up and absorb all the gold and silver, but not any other metal, and then it can later be recycled. After 7 hours, the mercury and water in there was slowly emptied through a small porthole in the barrel into a piece of machinery on the floor below called an alterator. In a process similar to a cream separator, in the sense that all the liquids swirl around on the inside, throwing the water and any light material to the side, this allowed the heavy mercury saturated with gold to drop straight into the bucket at the bottom. Then, to our right here, we have the amalgam press. The mercury gold mixture was poured into the top, and compressed air was supplied, which forced the excess mercury to pass through the filter and drop into a bucket of water. The product was a semi-hard cake. The circumference of the press and several inches thick, depending on how much gold was present. The color was pewter gray since the gold particles were still covered with a thin film of mercury. The substance was called amalgam. The word actually means mercury mixed with metal. You can also make a silver amalgam or a copper amalgam since mercury will pick up these metals as well. Here is the retort, the last of the 5 steps in refining the metal. So you would take the amalgam cakes, as you can see there, and they were broken down into small pieces and placed in those steel half-moon vessels called boats. And then they were put into the retort oven and fired for 12 hours at 1200 degrees Fahrenheit to completely drive the mercury off. And then it would be turned off and allowed to cool for another 12 hours. The product of this was called a sponge. It was about 70 to 90% gold, with the remainder mostly silver and some copper. This was as far as the company processed their gold here, but you will see they installed in the very last year a bullion maker that would process it further. Here is the bullion furnace where all the material was melted and it would separate according to weight, with the heaviest on the bottom. And the first thing out of it would be the slag rock, and then the next would be the lighter metals, but very last would be the gold at the very bottom, almost in bullion state, 99% pure, poured in the cast iron bullion bar containers, as you can see down there.
Thank you for watching this very long episode of The Chemistry Question. Be sure to subscribe, leave any questions or suggestions in the comments below. Hopefully now you know all about gold mining and processing, and as your reward for staying through this entire video, here's a little bonus clip.
Only on a mine tour.